Hi, welcome to Discrete Structures. Today we're doing section 1.5, which is about functions. So let's just put it in context. Beforehand we saw sets, we saw operations on sets, we did lots of things with sets, and now what we're going to see is how you go from one set to another set, and that's called functions. Now, you've seen functions before, but mostly you've seen functions that go from the real numbers to the real numbers. That's what you did in high school and in pre-calculus and calculus. So let's give you some examples of some functions you saw. Okay, so f of x is equal to 3x squared minus 5x. G of x is equal to x squared. H of x is equal to square root of x. These are all things you probably saw. Now, I just want to show you some notation that the book does. H2 of x could be something like log of x, log of x. Okay, the 2 here is just a subscript. So that's part of getting used to mathematical notation. It doesn't mean anything. It just, I had an h here, so I wanted to make another h. And you might have something else called like h3 of x. Well, you know what? Let's make it just more interesting. h3 of y. Okay, and that's equal to sine of y. Okay, we're not dealing with these functions anymore. You dealt with them in high school, but we're going to deal with them with a more general thing. The main point of all these things is if you plug in a real number into here, you're going to get out a real number here. So let's say you plug in the number 5. 5 into this function. 5 squared is 25. 3 times 25 is 75. 75 minus 25 is 50. Okay, so f of 5 is equal to 50. Let's do this one. If you plug in 10 here, you're going to get g of 10. You get out 10 squared, which is 100. Okay, any real number goes into any of these, and you get out a function, and you get out another value. So you plug in a number from here to a number from here. Now we're going to generalize that. That's what you saw before. Now we're going to generalize that, and we're going to talk about two sets, S and T. Okay, just pictures of the sets. And now you're going to have a function f from S to T. This is what a function does. It takes an element in here and it gives out an element in here. So you might have a little element here, S, and it's going to go, this function is going to take that little element to f of S, which is, let's say, little t. Okay, so this is a little element in capital S, little s in capital S, little t in capital T. Okay, we're going to see lots of examples, but first let's give a formal definition. Okay, definition. I just want to say the rest of the book uses functions. Functions show up everywhere and anywhere. It's a central idea. Definition. A function f. So this is what we're defining. A function f from set S, that's S, to set T. Okay. What is it? Assigns to every element S in set S a single element T in set T. That's what it does. It's an assignment. It's just, this guy goes to that guy. That's it. Nothing complicated. We write this function like this. F colon S to T. That's where it starts from. That's where it goes to. That's where it gets the input values. That's where the output values are. Okay? And so we have something very similar to that. Okay, so let's look at some examples And the examples are somewhat babyish, but they're real world. They're not mathy examples, they're real world examples. Okay, so you have the set of books in the world, and every book has a people. This is the set of people, and to every book they have the author. So a book has an author. Okay, so any book, there is a person who is the author. It doesn't go the other way. Not every person wrote a book, but every book was written by a person. So to every book you can assign it. Now we have a problem. What happens if a book is written by two authors? So then that won't deal well with this single element. So that's not a function. So we have to change this a little. Let's say first author. So take any book. Could have one author, or it could have 15 authors. The first author is a person. Okay, so that's a function. It takes a book, outputs a person. Okay, let's do another example. People. People. This goes a function from it to itself, just like we had the real numbers going from it to itself. Okay, and mother. Every person has a mother. Okay, so this is all people living or dead. Okay, let's do some other, again, these are real world examples. We just want to get used to it, then we'll do some more mathy examples. Okay, so U.S. citizens, there's 300 million of those. U.S. states, United States states, there's 50 of those, and there's a function. Every citizen lives in some state. So we'll say lives in. Now that's not really there are certain U.S. citizens who don't live in the United States. They're expatriates, whatever, but we're going to leave that alone. Okay? To every I, take the collection of all i's, okay, we write the function like this too. So we can write it like this. Okay, but we're going to write the function, we're going to write the name of the function on top, and we're going to have the word people. Okay, every I in the universe belongs to some person. So every I belongs to a person. Okay, fine. Noses belongs to a people. Every person has a nose. But these two functions are interesting. They're both, I don't know, this doesn't have a name. These are two functions. Every I, it assigns to the person that it belongs to. Every nose assigns to the person it belongs to. But we're going to see later on, these two functions are different because there are two I's that can go to one person. But every nose, there's only one person that has that nose. So this is a little bit more unique. To every nose, there's exactly one person that has that nose, and no one else is that person. There's only one nose per person. There are two eyes per people, and we're going to see that later on. We're going to make that distinction. Okay. Okay, so now that we have the intuition of what a function is, let's do some more definitions and things like that. Okay, definition. Let's say you have a function s to t. Okay, f is defined on s with, this is just English, values in t. So we say it's defined, it's defined on S. In other words, it gets its inputs from S with values in t. Its outputs are in t. So we write it like that. That's, again, it's English. Okay? What we say is S is the domain of f, In other words, so this is the word domain. This is where it's defined, is the domain. This is where it's home, in some sense. Okay? And T is the book uses this notation, so we're following the book. The codomain of F. Okay? So if this is the domain, this is called the codomain. The word co just means the other side. Okay? Great. Next. There is an image. I'm sorry. Hold on. There is a subset of T called the image of F. Okay, so F goes from S to T. There's a subset of T called the image of F. We'll see what that means in a second. Basically, it goes as follows. Here's your set S. Here's your function F. Here's your set T. There's a subset of T, and we call that the image of F. We write it im of F. Okay? And what is this subset? It's all the things that have values in T. In other words, not everything in T will be the output of this function. So if we look at the outputs, image of F is all the outputs of this. Take everything in here. What are the outputs? Things out here are not hit by the function. They're not the output. Things in here are the output. We have to see some examples. Okay? So this is called the image of F. This is called the domain. The set is the domain. The set of outputs, of possible outputs, is the codomain. Okay? And sometimes we write it like this. S is equal to the domain of F, and T is equal to the codomain of F. Okay? So we need some examples of this. Let's just go through the examples. We saw mother, the function mother, the domain is people, the codomain is people. For the function the U.S. citizens, lives in, the domain is U.S. citizens, the codomain is the states that it lived in. Okay? Okay, great. Okay, so we had a function g, and g goes from the real numbers to the real numbers, and g of x is equal to x squared. That's a very nice function. The image of g, what does it mean? The possible outputs of this function is equal to the real numbers star. Okay? Or another way of saying the real number star is those x such that x is greater than or equal to 0. That's the this set is the possible outputs. We can also write this set as follows. From 0 till infinity, round bracket. Okay? Okay. Okay. How about this? We had a function h, I don't remember. I don't even want to write it. We'll write it like this. Image of the sine function. Again, we're not doing trigonometry here, but the image of the sine function, the possible output is the interval from -1 to 1. Okay, remember the sine function does this. Okay, here's your 0, here's your positive 1, here's your negative 1. Any possible output from -1 to +1 is the image. So this is a subset but not equal to the real numbers. Okay, so these are images of your function. Okay, let's go to our baby examples. Those were the real numbers. Those are functions from the real numbers to the real numbers. Let's go through baby examples. We had a function from books to people called first author. Okay, first author. Well, not every person wrote a book, but there is a subset of people who are the first authors of some books. Okay, so this is the first authors of some book. Okay, so if you wrote a book, you are the first author of that book. Okay, so that's the image of this function. We had mother. So here we have people. Every person has a mother. So there are the subset of human beings who are mothers. That's the image of that. Okay, not every person is a mother. Okay, let's do the U.S. citizens. We had U.S. citizens, and we had lives in one of 50 states, U.S. states. Well, every single state in the United States has some U.S. citizen living there. Even Montana, I think, has 3 people living there, but I think it's the smallest state in terms of population, but even they have people living there. So what that says is that the image is equal to the codomain. So it's the whole thing. Okay, we'll have another name for that also. Okay, great. Okay, you're reading the book also, and the book talks about the absolute value function. Absolute value function. Okay, so 5.3 is equal to 5.3 minus 6.1 is equal to 6.1. Okay, so this is a function from the real numbers to the real numbers. Okay, and we write it like this with the 2 bars. Takes a real number, outputs a real number, but the image of this absolute value function is the interval from 0 to infinity. Positive numbers. Only positive numbers can come out of this function. Okay. Another function that the book talks about is the floor function. Let's just remember what the floor function is. Take 5.3, look at the floor of that, that's equal to 5. Take minus 6.1, look at the floor of that, that's equal to minus 7. Okay, we go down 1. Okay, so this is a function, the floor function. Okay, is a function. It takes any real number as the input, and its output is z. Positive or negative integers. Okay, the image of this, the image of the floor function, well, anything could be seen as the output is any positive or negative integer, so that's z. Okay. Okay, great. So the book talks about this. You're reading the book also. Let's go on. Okay. The book also sometimes describes a function like this. Here's your set S. This is for very finite sets, very small sets. You can do this. This guy goes here, 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 this guy goes here. So you can describe a function with these little arrows showing you. In this case, by the way, there could be another thing there that gets nothing. Therefore, this function from s to t, the image is these 4 elements, not this 5th element, because it wasn't hit by anything. Okay? Okay. Okay, great. Okay, now I'm going to use a phrase, I'm going to use a word that you've seen, but you've seen it, you think it's something different. Okay? But it's actually the same. So let me just say it the way you've seen it before. We had a function g of x, which is equal to x squared. And your 9th grade teacher and your 10th grade teacher and your 11th grade teacher and your pre-calculus teacher asked you for the graph of f. Okay? And you had to spend a lot of time doing that. Okay, so this is g. That's the graph of the function. Okay, so now I want to do that, but not talk about a function from the real numbers to the real numbers. This is a function from the real numbers here to the real numbers here. Okay, rather I'm going to talk about a regular function, a generalized function that we've been talking about. So, ready? So this is what we saw before, and I'll show you what it means in a minute. But let's say you have a function f from s to t. Then there is a set called graph of f. Okay, let me show you what it is. It's equal to those x comma y member of s cross t. Oh, we saw this last time. What's s cross t? These are ordered pairs. Okay, all possible ordered pairs. So here you're going to have an input and an output, such that f of x is equal to y. So here's this set. It's a set of ordered pairs, okay, where this is the input and that's the output. This is the domain of the function. This is the codomain of the function. This whole set is a subset of s cross t. Okay, great. Let's do a baby example of this. So, an example. This is an example also, but we'll see that in a second. Example. Okay, you're going to have S is equal to the set A, B, C. You're going to have T is equal to R, U, V. Okay, and now you have a function f from S to T, and I have to tell you what its value is. So f of A is equal to R, f of B is equal to U, f of C is equal to R. So here's a nice example of a function. Here's a very nice example of a function, and now what I'd like to do is show you what the graph of this function is. Okay, so let's write it out. Graph of f is equal to pairs of things that start from one and go to the other. Okay, so we write it like this. You ready? A goes to R, B goes to U, C goes to R. This is the graph of this function. Okay? Okay, great. So now I want to show you how this fits into this concept. It's the same concept. You ready? What is this line? What is this line? This line right over here. So every point of this line is what? This is x, and this is f of x. Okay. This point is little x comma f of x. Okay. And this point, let's say here, this is x prime, and guess what this is? This is f of x prime. Okay. So when you were in 9th grade, 10th grade, and pre-calculus, and you're making this graph, what are you doing? What you're doing is you're highlighting the elements, that's this guy, you're highlighting the elements that are in the graph. Okay, so let's go through this. This is the real line. This is the real line. This whole plane is the real line cross the real line. Okay, great. Now you have a subset of the real line cross the real line, which is this line, which is the graph of G. The graph of G is a subset. We describe that, so here's the real line, here's the real line. This whole plane is R cross R, and you have a subset that you highlight like that. That's this line that highlights this graph that shows you what the inputs are and what the outputs are for this graph. So this is something that you've seen a lot before, but you didn't know that it was really this thing. So that's what we're here to show you. It's really just subset. What's this subset? It's a subset of S cross T. Okay? Okay. Let's be more careful. No, let's not be more careful. Let's do another example. Okay? Again, a babyish example, but very nice. You ready? S is equal to 1, 2, 3, 4, 5. Very easy. T is equal to 5, 6, 7, 8, 9, 10, 11, all the way till 18. Sounds good? Now I'm going to talk about a function from this set to this set. F goes from S to T, such that f of x is equal to 3x plus 2. Okay, and now I want to look at the graph of f. Okay, so we have to plug in some values. So the graph of f is going to be ordered pairs from here and here, such that, let's see, if I plug in the number 1, what's the output? 3 times 1 is 3 plus 2 is 5. Next, if I plug in the number 2, what's the output? 3 times 2 is 6 plus 2 is 8. Just to do things not in order, because it doesn't matter how you list elements in a set, 5 times 3 is equal to 15 plus 2 is 17. So 5 comma 17. Okay, let's do 4. 3 times 4 is 12 plus 2 is 14. 3. See, we did this out of order. 1, 2, 5, 4. Let's do 3. Okay. 3 times 3 is 9 plus 2 is 11. This is the graph of this thing. Now, we can actually make it into a picture if you want. Okay? So we're going to make it into a picture. Ready? So we're going to have like this. S is the set 1, 2, 3, 4, 5. T is the set 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Hold on. And now we're going to highlight the graph, just like we did with that parabola. You ready? 1, 5 is right over there. 2, 8 is right over there. 5, 17 is right over there. 4, 14 is right over there. 3, 11 is right over there. Okay. By the way, that looks like a straight line. That's because this function is a straight line. I did it upside down, but that's okay. Usually you think of this straight line as going this way, but it doesn't matter. Anyways, these points are the graph of this function. Okay, great. Let's go on. Okay, so let's ask a question. Question. Is every subset of S cross T a graph of a function? Okay, let's do this again. Let's explain it again. You ready? To every function from S cross T, you have, so for every function f from S cross T, from every function f from S to T, you have a graph of f, which is a subset of S cross T. And now I ask the following question. Is every subset of S cross T a graph of some function? And the answer is no. Okay, so let me give you an example. Okay, I want to show you what makes something into a graph. Okay, so let's do the following. Let's say S is equal to A, B, C. We just had that a few minutes ago. T is equal to R, U, V. Okay, and now I want you to consider the following subset of S cross T. Ready? A, U. B, U. A, V. C, R. Okay, this is a subset of S cross T. It is a subset of S cross T. Okay, what's S cross T? It's ordered pairs where the first elements are in S. That's true. A, B, A, C. Okay, and the second elements are in T. U, V, R. Very good. So, is this subset of S cross T? Is it a graph of a function? Okay, stop, shut the video, think for a second, and you'll see the answer is no, it's not. Why? Because what's the output of A? Is it U or is it V? Okay, and the answer is this is not a function because it has two outputs of A. Remember, the first thing is the input, the second thing is the output. So A, if you input A into a function, you're going to get out U. If you input B, you're going to get out U. That's okay. If you input A, you get out V. What is it? Do you get U or do you get V? You're only allowed to get a single thing. So this is, it's a perfectly legitimate subset of S cross T, not a function. Okay. Okay, ready. So let's try another one. How about this? How about A, U, C, R? This is also a subset of S cross T. Question. You ready? Question. Is this a graph of a function? And the answer is no, it's not. Why? Because this basically says f of A is equal to U, and f of C is equal to R. That's very good. But what are we missing? We're missing f of B. What's a function? It assigns every single element of the first set an element of the second set. This graph, this subset, didn't assign a b, a value to b. Therefore, it's not a function. This subset is not from a function, not from a function. Okay. Okay. So now we stated the question. We went through two examples of where things fail, get a negative answer. Now let's give a positive answer. Let's explain to you when it is. So, in order for a subset G, subset of S cross T, to be, you know what, let's not write to be, let's write that, to correspond to a function from S to T, we need, okay, I really want you to get this concept of a graph down pat, so that's why we're doing this. We need for each x in S exactly one y in T such that x comma y is a member of G. Okay, so you saw 2 seconds ago that problem where A goes to U and A goes to V. Okay, we don't like that. So we need for each x member of X exactly one y member of T, such that x comma y is equal to 1. X comma y is in the graph. But you can't have more than one. You can't have more than one. You can't have two. You can't have x comma y and x comma y prime is a member of G. That's not kosher, because this is not a function, because x here goes to y and x goes to y prime. You're not allowed to have that. Cross it out. Bad. Okay? But exactly one means one, not two, definitely not 3. Definitely not 3. Bad. Okay? Well, what else does exactly 1 mean? It means not 0. So we have to have also, you have to have for every x, you have to have something in there, exactly 1. So it has to have some value y. You can't just leave it out. And that was the second problem we had with that, with those two sets. We had only one thing there. That's not good. We had a 0 thing. We had something for A and we had something for C. We didn't have anything for that. Okay? Notice there's no problem with having x comma y member of G and x comma y prime. Shoot, nope, sorry, hold on. X prime comma y member of G. This is not a problem. Okay, what this says is the output f of x is equal to y and f of x prime is equal to y. That's not a problem. Okay, two things going to the same output value, that is not a problem with us. Okay, why is it not a problem? Because let's just talk about mothers. You can have two siblings, okay, and they have the same mother. So that would be the same mother. You could have two books written by the same person. Not a problem. What you can, I'm sorry, we're talking about the first author. What you can have is one book having two first authors, not legal. Okay? And what you also can't have about the mother, you can't have one person having two biological mothers. Not legal. Okay? So this is okay. This is not okay. One object, two different inputs going to the same output, that's okay. One input having two different outputs, not okay. Okay? Okay. So this gets the idea of a function really down pat. Okay, great. So we introduced the notion of a function. And like I said, we do this over and over. We're going to now do something different. Namely, we introduced the notion of a function. Now we're going to do something different. We're going to talk about special types of functions, just like we talked about special types of sets. And then we're going to talk about operations on functions. And then we're going to talk about properties of these operations on functions. Okay? Okay. So, special functions. Special functions. We're only going to talk about one special function. Okay. It's called a characteristic function. A characteristic function. This is a function that characterizes something. It describes a subset. Let me explain to you. Okay? You have A is a subset of S. Okay? And we're going to make a special function called like this. And that's a Greek letter chi. Okay? And you're supposed to think of the word characteristic. So chi characteristic. Okay, fine. Anyways. And this function goes, this is a subscript. It describes this function. It's chi subscript A. Okay? And what this function is going to do is going to describe that subset A. So, sorry, that's wrong. Hold on. The output of this characteristic function is 0, 1. Okay? Okay. Let me give you the intuition first. Okay? Because we're all computer programmers, so let's think about it. You want to describe something. You have a set of customers. You want to describe if they're male or female. So you might make female 0 and male 1. So instead of writing the word female or instead of writing the word male on your record, you just have one bit, 0 or 1. And that's what we're doing here. Okay? The output is 1 bit, 0 or 1. Okay, so let me describe to you how this function works. The characteristic function of A takes as an input a little element here, S, okay, and it outputs either 0 or 1. 1 or 0. For S in A, sorry, okay, and if S is not in A. Okay, so this function tells you, okay, which of the elements are in A and which of them are not. If it outputs a 1, it's in A. If it outputs a 0, it's not in A. So this function tells you bit on, bit off, 1 or 0, whether or not what every element is. Okay, so now we have to do a little bit of an example. Oh, first I want to draw a picture. I like drawing a picture of this. Okay, basically you have this. You have a set S. You have a subset A. Okay, well, everything in that set A goes to the number 1. And this might not be good. Not the best picture in the world. Everything else goes to the number 0. So if you're in A, you go to the number 1. If you're not in A, you go to the number 0. Not the best picture, but not so bad. Let's do an example. You ready? Okay. You have n, the natural numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., etc. You have a subset of those called the prime numbers. 2, 3, 5, 7, etc. Okay, great. So now I want to characterize that function. I want to tell when a number is prime or not. So we're going to write that PR. Okay, so let's see what we have. The number 6. Question, is 6 a prime number? The answer is no. Okay, but the number 7 is a prime number. The number 2 is a prime number. The number 39 is not a prime number. Okay, 39 is 3 times 13. Okay, great. Okay, let's do another one. Okay, think of the set of Brooklyn College students, and we have the subset of that of our class. Okay, and now you want to characterize our class. You're making from a subset into a function, okay, and it goes from BC students to the set 0, 1. You might have true, false, or if you want. And basically, every one of you who are registered in the registered students for this class, our class, they output a 1. Those people in the hall do not output a 1. Okay, great. So characteristics functions are nice functions. They show up all over. They're important, and especially important for computers because we describe subsets by giving such functions. Okay, great. So we dealt with a special function. Now I want to do an operation on functions. Okay, so let's do this. This is a special type of operation. Consider two functions. F goes from S to T. G goes from T to U. U is not the universe. U is just another function. Okay? So, notice this is the same as this. So we can draw this situation as follows. You have three sets, S, T, U. You have a function f from S to T. You have a function g from T to U. It's a capital U. Okay? Now, I want to make a new function. I want to compose these functions. I want to do this and then do this. Okay? And so, just think of this. We're going to make a new function from from S to U. And basically, this function is a composition of these functions. It does this and this. For computer programmers, we have no problem with that. You have a function that consists of two other functions. Do one function, then do another function. That's exactly what we're doing. We're doing one function and then another function. We call this F compose G. I wrote it in the right order. Okay, let's see how this function works. Well, you're going to have a little element here called little s. It's going to go to a little element here called f of little s. Now, G takes little elements here and brings them to there. What should that be called? We'll call that G of f of little s. That's a little element in there. G of f of little s. I wrote G circle f, that's the operation, this compose operation. I wrote it because here we have G f. Okay? Okay, let's be exact. G composed f is a function, and it goes from s to u. Okay, and now I can describe how it's defined. G composed f on a little element s is equal to G of f of s. Okay. Okay, let's do some examples, but the example I'm going to do is a little bit of a funny example because it goes from, both functions go from the reals to the reals. So we're going to have a function from the real numbers to the real numbers, and then we're going to have another function to the real numbers again. So we're going to call this f, and we're going to call this g. Okay, so let's do this. F of x is equal to x to the third minus 17x. That's a silly function. I'm sorry, I don't want to do that function. Hold on, we'll get to that later. I want to do this. 3x squared plus square root of x, and then g of x is equal to 1 over x. Then I want to show you what G composed f is. On little x, it takes a number, and it's going to do G of f of x, okay, which, what's f of x? Well, that's equal to G of 3x squared plus square root of x. Okay, great. Very nice. Well, what does G do? G takes the input and puts it under a 1. So this becomes 1 over 3x squared plus square root of x. This is what this function does. It takes an x and outputs that. Okay. Notice this is different than f of g of x. Since they both come from the real numbers and go to the real numbers, we can do this also. G f. Okay. No. Yeah. Okay, so let's do this. This is equal to f of g of x, okay, which is equal to f of 1 over x. That's what g does. It changes x into 1 over x, okay? And so this becomes 3 over x squared plus the square root of 1 over x. Okay? Now this function and this function are not necessarily equal. Okay? So this is not usually not equal. Okay? And what we say is composition is not commutative. Okay? So we had this notion of a commutative operation. Addition is commutative, subtraction is not. Union is commutative, relative complement is not. So here we have f composed g is not equal to g composed f. Okay, let's do another example. Okay, here's another example. F of x is equal to x to the third minus 17x. G of x is equal to 3x squared. Okay? Then G composed f of x is equal to G of f of x, which is equal to, plug in f, this is going to be G of x to the third minus 17x. Now we do G of that. This is equal to 3 times x to the third minus 17x, and then square it. Okay? And you might have to work out all the details of this. Not interested in doing it. Same thing here. F composed G is not necessarily going to equal to G composed F composed G. Okay? So it's not commutative. Well, function composition is not commutative. That's interesting, and then we're going to see a lot more examples in the homeworks, but let's do something else. Let's say I have 3 functions, which means I have 4 sets. So we can call this S, T, U, V. And now I have 3 functions. F, G, and H. Okay, let's see what this means. Ready? I can compose these 2 functions, and we'll get F composed G. Now, this is a new function from S to U. Great. I can take this function and I can compose it with that function because they're one after another. So I can compose these functions, and I get F composed G, that's in parentheses, composed H. Very nice. Okay, that's one thing. Next, what about these 2 functions? I have 2 functions right next to each other. When you have 2 things next to each other, you can associate them. So let's associate them. So this is G composed H. Okay, great. But now I have 2 functions that are next to each other. F composed G composed H. So we can do this, we can compose these with this. And we get another function like this. And it goes as follows. F composed G composed H, but this is in parentheses. Okay, so now I have a function from S to V like this, and a function from S to V like this. Okay, it turns out function composition is associative. It's not commutative, but it is associative. This is equal to this. Let's write it out like this. H composed G composed F is equal to H composed G composed F. It's the same function. Why? Very simple. How do you describe these 2 functions? They're both the same thing. They both equal to the same thing. Okay? They're both equal to the function H of G of F of little x. Okay? Basically, you have a little guy in here. It goes to here, which goes to here, which goes to here. I don't care if you do it this way or this way. They're the same thing. Okay? One more idea, and we'll call it quits for this section. We're going to see functions again in section 1.7, but let's just deal with one more idea. For every set S, here's a set S, there's a silly function. We call it the identity function. Now you remember we saw the word identity. We talked about identities here. X plus 0 equals X. X times 1 is equal to X. We had those identities. So we're going to see something very similar to that. We're going to call this the identity function. And you write it, the book writes it as follows. 1 slash S. This is a function from S to S. 1 subscript S. Now, you should think of it as this guy. Okay? Okay? Now let me tell you what this function does. 1 of s on little input s, here's a little input guy in here, okay? The output is the world's silly, this makes it the world's silliest function. Stupid. It's a stupid function. The output is s. The input is the same as the output. Okay, great. Okay, so we have a simple function, and the input is the same as the output. Now, I want to show you something cute. Let's say we have a set S, and we write the set S again over here, and we write this as 1 of S. This is the identity on S. This is the stupid function that whatever you input here outputs the same thing. Okay. Now you have a function f. Goes from S to T. Okay. And now I ask a basic question. What is f 1 of S? What's the composition of f compose S? Okay, and the answer is very simple. Look what this does. This takes S and goes to 1 of S of little s, which is equal to little s. And now you do f of it. Now you take f of that. So that's going to be equal to f of little s. Okay, so when you do this composition of these two functions, you get out the same function that takes s to f of s. Takes little s to little f of s, which means that this composition is simple f. So f circle 1 of s is equal to f. It's the same function. You do nothing to it here, and then you compose that with doing a function. You do a process that does nothing, and then you compose that with f. That's the same thing as doing f. Okay, great. Hold on one second. So this should remind you very much of this thing that we saw. X times 1 is equal to x. So here, that's multiplication. Here's function composition. And what we're saying is this identity function does nothing or doesn't change anything for function composition. Great. Let's just do something very similar to that. Let's say you have a set S, and you have a function from S to T. And then you have the silliest function in the world, the identity on T. What does the identity on T do? It just takes whatever little t you have here to the exact little t, the same little t. It doesn't change anything. Now we ask the following question. What is the composition of f composed identity on T? Okay, let's see what this function does. It takes a little guy here, S. It takes it to f of s, which is a little guy t, okay? And then what does it do to that little t? It takes it to that little t. So basically this goes from s to t, which is exactly what f did. So this composition, f followed by 1 of t, is the same thing as f. So we get f is equal to f composed t. Again, same thing like here. When you multiply a number by 1, it doesn't change it. It gets the same thing. So when you compose with the identity function, you get the same thing. Okay, so that's the end of functions. Again, functions show up all over. Every single place in computer science, in math, physics, everything. Enjoy. Have a great day.